Hello everyone, welcome to the lecture series of pattern classification. So in the last lecture, we observed that the cost function j0x0 is minimized by choosing x0 as the sample mean. But the sample mean is basically the zero dimensional representation of the data. So that means sample mean does not reveal any variation in the data. So to consider the variability in the data set, we must consider at least one dimensional representation by projecting the data onto a line running through the sample mean. So let us try to understand this. As I said, to consider the variability in the data set, we must consider at least one dimensional representation by projecting the data onto a line running through the sample mean. So what do you mean by this? So for this we can consider that let E is basically a unit vector. So unit vector means that magnitude or norm, it should be 1. Okay. So this unit vector is basically in the direction of the line. That means this line is basically the one dimensional representation. So let us draw some data, then it will be clear to visualize it. So set of data are something like this in the two-dimensional feature space. This is the two-dimensional data. Then we want to map this two-dimensional data to one-dimensional representation. So we have to project the data on to a line, and that line will be basically something like this, and this line is basically in the direction of E, that is the unit vector in the direction of the line. So this is basically the unit vector. So we can write the equation for this straight line as x equal to m plus a e. So just you notice here we have some additional term which is basically the one dimensional vector. So in the previous case we had x equal to m, okay. So that was the zero dimensional representation, that where the variation was not there. So now we introduce the variation where a is basically any real value which corresponds to the distance of any point x from the mean M. So, let us take one sample, suppose this is x. So, this is the basically the distance, if somewhere mean is this one, this is the mean, then it will compute the distance A. So, this will be the A. Okay. So, now this is for only one sample. So, we can have the n number of samples. So, basically that x1, x2, xn, these are the n number of samples, and basically this is from the d-dimensional feature space. So, we can write a very general expression, that means k is the index. So, it will from, that means xk equal to mean plus ak, and E is the direction of the line, and that is basically the unit vector. Then we can find the optimal set of coefficient. Then we can find the optimal set of coefficients ak by minimizing the squared error. Okay. So, what is the squared error? Squared error criteria function. So, how we can write? Now, this is basically the cost function that we need to write. So, J1, so this time we are writing 1 instead of 0, because in earlier case 0 dimensional representation was there. Now, we are representing the data samples using 1 dimensional representation. So, this is the cost function for 1 dimensional representation. So, that is why J1. And then we have the different coefficients as well that need to be find, that means optimal value of these coefficients, and also we need to find the unit vector, the direction of the unit vector, so that this cost function can be minimized. So, we have to just put in the previous expressions that we have already seen. So, what was that? So, here okay, we have to compute the square error x minus xk. So, already we have seen this expression, but we have to put the value of x as the equation of line. So, x equal to m plus ak e minus xk square summation over from k equal to 1 to n. Now, just rearrange the terms. So ak e minus xk minus m. So here just we rearrange the term. Now we can compute the square of the given terms. So ak square vector e square minus 2 ak e transpose xk minus m. One thing it can be noticed here, that here we have written E transpose, because E is basically the column vector and we are making it row vector, so that the computation of this term will give you the one scalar quantity. So the cost is basically one scalar quantity. That is why it is E transpose into xk minus m. Then the next term will be so here you can recognize that this is the unit vector, E is the unit vector. So magnitude of E is basically 1. Okay. So we can put here and we will try to solve this problem, because we have to minimize this cost function. So what we have to do for minimizing the cost function, partially differentiating J1 with respect to AK and setting the derivative to 0. Now we have to take the derivative of this term with respect to a1, a2, an, and then we will equate to 0. So let us take the value of the derivative of j1 with respect to ak, and then we will equate the term to 0. So you observe here that this term is independent of ak, yes, and this term will be 1. So ak is available in this term only, and here ak is available. So we can write j1, so this is basically the partial derivative. So j1, the derivative with respect to ak. So what will be the term? So it will be summation twice ak, the first term. In the second term, so it will be twice. So ak will vanish now. So E transpose xk minus m k equal to 1 to n, and the last term will be 0 because last term is independent of ak. Now we need to equate to 0. So solve it. So when we will solve it, we will find that ak equal to E transpose xk minus m. Here this obtained solution only says that we obtained a least square solution, because we try to minimize the squared error term. How? By projecting the vector xk onto the line in the direction of E, and that passes through the sample mean. Okay. So now let us put this value in the previous expression. So what will be the expression? J1 E, because already we minimize this term with respect to A1, A2 and AN, but only the left term is E. So for the given value of A1, A2, AK, we have the minimum value of J1 as square minus 2 summation over AK square, because we have substituted this value here. In the previous term we had only A into E transpose xk minus m. So we substituted this term, then it become the AK square plus summation from k equal to 1 to n xk minus m square. So just simplify this term. So here from these two terms we can write that summation n k equal to 1. So here only one AK will be remaining and we will put the value of AK. So it will be e the power transpose xk minus m square. So basically this is the AK and this is the AK square. So here we just substituted this value plus summation xk minus m square k equal to 1 to n. So we can expand this term. So when we expand this term, it will become minus summation e the power transpose. So again we have to maintain the dimensionality of the matrix multiplications. So here we can write minus E transpose S E plus summation from k equal to 1 to n x k minus m square, where S is summation over xk minus m xk minus m transpose, where k equal to 1 to n, and this is called basically the scatter matrix. So we can define this scatter matrix as that n times the sample covariance matrix. Okay. Now our resulting cost function is basically J1E equal to minus E transpose S E summation k equal to 1 to n xk minus m Euclidean norm square. Now we have to minimize this cost function with respect to E. Here you can observe that this term is independent of E. So that means we need to minimize this term, we need to or we need to maximize E transpose S E, because here negative sign is there. So we can formulate one problem of the maximization problem, that is basically we have to maximize E transpose S E such that the magnitude of E is basically 1. So here from this a Lagrangian multiplier can be used to solve this problem. So what is Lagrangian multiplier? So this problem will be formulated as U equal to E transpose S E minus lambda E transpose E 1, where lambda is Lagrangian coefficient. So I will make another video lecture for the solution of this kind of problem using Lagrangian multiplier. For now you can just remember that this is the equivalent problem using the Lagrangian multiplier. So we can maximize this term. So what we have to take? We have to take the derivative. So del u by del e equal to 2s e minus 2 lambda e. Okay, and we need to equate to 0, and from this we can obtain that s e equal to lambda e, and this is basically very important result. Here you can observe this expression is that already we know. From this expression we can conclude that S is the basically the scatter matrix and E is the eigenvector and lambda is the corresponding eigenvalue of this scatter matrix. In particular, it follows that to maximize E transpose SE, so we have to select the eigenvector E corresponding to the largest eigenvalue of the scatter matrix lambda. So that is the basically the inference from this solution. So to find the best one-dimensional projection of the data, we project the data onto a line through the sample mean in the direction of eigenvector of the scatter matrix having the largest eigenvalue. This is the inference that we need to remember. That is very important point. So this one-dimensional result that we just obtained can be extended from one-dimensional to d-dimensional projection, but we have to substitute x. So we have to substitute this x value to compute the cost function, where d dash is less than equal to d, and then it is not difficult to show that criteria function. So we have to define the criteria function for d dash dimensional space. So this is the criteria function, and the solution of this criteria function will be that means this will be minimized only when the vector E1, E2, Ed dash are the d dash eigenvector of the scatter matrix having the largest eigenvalues. So because the scatter matrix is real and symmetric, so these eigenvectors are basically the orthogonal vectors, and also the coefficient ai are the component of x and are also called the principal components.